the Innovation Program. He's going to be speaking about probing heterogeneous TD materials for the next graphene superconductor. So we do see some overlap in our discussion today. Wonderful. Welcome, Adam.
Thank you, Natalie. So I had the pleasure of working with a grad student and for the majority of my time at Stanford 2 summers ago, and my PI was Ben Feldman. We worked tirelessly for 2 months exploring some really small materials. And this was through the Ignited Education. So you know about insulators and conductors. You probably heard about semiconductors and Intel chips, and I'm sure you've heard about superconductors. You know, the materials that allow the free movement of electrons, but this actually isn't really about all of that. This presentation is about surprises and the kind of surprises that scientists live for. So in that underground lab at Stanford University 2 summers ago, I learned that the properties of materials depend on the arrangement of the atoms, but also upon the interactions of the electrons. In rubber, one electron is bound to a nucleus, and therefore it doesn't allow for the flow of electrons through the material. In a conductor, on the other hand, there's usually a delocalized electron, and that electron is free to move through the material, but there's always going to be resistance. And these materials typically, in our experience, are 3-dimensional, meaning there are no constraints for the electrons to move up and down between the different planes. So what happens, though, if you can fine-tune materials so that these electrons are constrained so that they actually can only move in one plane? And what would happen if you could stack these atomically thin layers of atoms on top of each other? What new, interesting, curious properties could emerge from that? And that is what my lab really got itself involved in. And that is one of the, I guess, newest physics questions being explored at the moment. So this property of graphene being a, there you go. So this idea of graphene being able to pull off these like atomically thin layers of it and the special properties, this was explored, I believe, earlier in the 2000s, but it's only 2 years ago that this idea of actually twisting these layers and placing them on top of each other was really, I guess, hitting the research publishing circles. The New York Times reported on it 2 years ago. So it's like entering the like mainstream consciousness at this point. But if I back up a step, if you take these sheets of carbon atoms called graphene, and typically they're electrical insulators. And if you lay one of these graphene sheets on top of each other and you twist it by 1.1 degrees, you get a superconductor. So normally these layers of atoms stack on top of each other in regular arrangements as defined by like the lower energy states. However, if you twist these layers into irregular arrangement, these planes that are going to now misalign, the electrons pair, and then you have some superconductive properties emerging. Again, though, this is really all at really low temperatures. So my lab took this one step further. In the lab I worked in, we actually didn't use graphene. We used tungsten diselenide and molybdenum diselenide, and we actually created heterostructures of atomically thin materials. So we took one layer of the molybdenum selenide, and then we stacked on top of it and twisted it with the tungsten diselenide. So the designer fabrication outlook for these materials are kind of limitless and endless. And really is determined by the interests of the researchers. So in the lab that I was in, I particularly was working with the tungsten diselenide. Now, I was literally peeling off, and you heard this earlier, the material from a tungsten, I was peeling off from a tungsten diselenide chip and with a piece of scotch tape and depositing it on layers of atoms one by one on a silicon wafer. While the process for cleaning these wafers was fairly established, my process was really experimental. Sometimes um, uh, I would pull the scotch tape off of it and then rub the tape to add pressure. And then other times I would add heat. But the takeaway for me was like under a microscope, you could look at these layers. I'm just going to skip through some of these slides. I think this is kind of the coolest piece here. So on the left picture here, you see underneath the microscope, and you can see that the transparency of the material is dependent on the thickness of the layers. You can apply a certain color set or set of color values to it and confirm that with an atomic force microscope. So these were some of the cool tools that I got to use while I was there in the lab. And it allows us to set a baseline for knowing when we have a single layer of atoms for stacking. So over time, perhaps scientists will be able to use the tunability of these systems to engineer the properties that they want materials one atom at a time.
Well done, Adam. Great presentation. Such an interesting research project that you had going. And while we're waiting for some questions to come in, I want to ask you, because I'm always interested in, where do you see yourself with this technology and your research, say in another year or two? What is your vision? That's a big question.
So I wasn't successful in creating one of these devices. I think I would love to get to the point that I'm succeeding in the fabrication of these devices so I can see if it actually works. So I can like take measurements. I'd love to be able to take measurements.
Okay.
Imagine. And Adam, did you get access to your lab? Did they work with you in order to have the hands-on time? Sounds like.
Yes, this was 2 years ago. And so I was working on campus, but it did take quite a while to obtain access to all of the different equipment.
Adam, we have a question from Lori Lancaster. There are many types or brands of Scotch tape with different adhesives and plastics. Did any particular type or brand work better for this mechanical exfoliation process?
Oh, yes. So the Magic Scotch tape for sure. It had to be like the brand name Scotch tape. And I remember it being like the green one. I don't remember what was special about it, if it was just made with more sustainability like ingredients, but the green Scotch tape.
And I'm also curious if, because I think about the Fibonacci deal in terms of how it spirals on itself. That just came to mind. I think about there's patterns in nature that constantly are working towards the spiral. And when you talked about that rotation of that 1 degree, I just wonder if, a mathematician or a physicist is going to want to get in on this particular research because of that interesting phenomenon that you guys found play out and be successful.
Mm-hmm.
Okay, is it for the questions, Gina, for Adam?
Yep, that's all I'm seeing. Does anybody else have a question for Adam? Okay,
All right.
Thank you so much.
Okay, our final presentation for today